All right. Just to keep you guys awake, we have a little quiz. Not exactly. We put our discussion questions in the form of online questionnaires that if you are a little too shy to answer, you can snap the QR code and answer questions. So we can only show them one at a time. But our first question, we wanted to get our discussion going, is do we expect the cosmic web environment to affect galaxy properties? So go ahead and register your opinion, and I'll close it in about a minute. So all you have to do is just scan that QR code, and you should have the poll up there. I'll wait until I see no more cell phones up in the air. You can. You can also do it on the laptop. Okay, going once, going twice. All right, closing the poll. Let's see how you voted. All right, okay, the majority of you said yes. One person, I think, said no. Would anybody like to justify their answer? Anybody? How about the person who said no? Would anybody like to justify that? I mean, I can think of one reason why maybe not, is that the scales are quite large, much larger than the scale of galaxies. But I see Phil back there has a comment. Just a second.
My question for you as discussion leader is, or the group, just like we've debated about, when we talk about environment affecting galaxy properties like morphology more traditionally, we've had years of arguing about what do we define environment by. And so, I think if the question was like, how much, do we expect the cosmic web to affect morphologies at fixed halo mass and assembly time, you'd probably get a lot more no's or something. But I'm just curious, like, what are the control variables? Yes.
Would you like to define some control variables?
No, I don't. I want someone else to.
Who would like to define some control variables? Joel. Okay.
Well, one obvious thing is to use density. So does the cosmic web spans a range of densities, but at a given density there are a lot of different cosmic web environments that could be filamentary or node or even sheet. So the question is, if you control by density, do you still see a cosmic web effect? And I think the answer to that is not clear. I'm co-author of a paper that said no for some things.
Okay. Pablo?
Just to be clear, I was the one that voted no. Just because we have to define it. At which redshift? I guess a very early universe maybe it doesn't affect that much. Maybe in a very late universe, again, doesn't affect that much, but it has been affected by the middle history. So, as usual, the questions normally are much more. The reality is much more complex than the question. So I answer no because at the beginning of the universe I don't see that affects that much.
All right. Anybody else have any comments?
So I think there are two types of effects from the cosmic web. I think there's the isotropic density effect, which Joe was talking about. But there's also the anisotropic effect, which, that I think is like the bigger cosmic web effect because anisotropically, right, like the angular momentum that's transferred has a very distinct geometrical, it's supposed to have a distinct geometrical signature. of accretion, which is very different from like, hot gas and clusters are part of, or nodes of the cosmic web. So, it's always important to think in terms of like, separating the sort of isotropic density effect from the anisotropic filamentary effect.
That's a good point to move on to the next
Okay.
question.
All right, let's move on. What do we need to improve cosmic web measurements in observations? So the poll should already be on your phone. Okay, I think we have a critical mass, so I'm going to end the polling, and let's see what you all voted on. Wow, look at that. Okay. Better filament definition or classifiers, as we already mentioned. And we still had lots of other choices here. Spectroscopic redshifts are sufficient. AI. I like AI personally. Where's Mark? Is he here? Something else. It's not. Some people said it's not possible to characterize filaments accurately in observations. Would anybody like to justify their answer?
Well, I'm one of the something else's, and the thing I worry about is redshift space distortions. So correcting for that, I think, is really important.
Yes. Does anyone have any thoughts on how to correct for redshift space distortions? Helen. Okay. Oh, Colin.
So this is a very naive question instead of like giving my answer, but I was wondering, for our purposes, whether it's possible to forward model the redshift space distortion instead of trying to correct it when it is maybe harder to do so.
Does anybody have any comments about that?
Of course it's possible to model. You just make backward light cones based on an n-body simulation, with all the hydra you want, and then take into account the peculiar velocities. So add the peculiar velocities to the flow. The problem is how to figure out how to do that from observations. It's easy to model observations forward, but the question was, how do we actually measure the cosmic web in observational data? And to do that, you have to undo that. Now, of course, one of the things you can use various kinds of AI for is to train by comparing the light cone to the physical space, the real space, redshift space to real space. And with enough examples, maybe an AI code could learn how to do it really well.
So there were a couple of people who voted it is not possible to characterize filaments accurately in observations. Does anyone want to comment on that? Anyone who voted that want to justify? Not brave enough? Okay, that's fine. Yeah, I agree. I think it would be very difficult, but there are a couple of ideas on how to do this.
Sure. So let's move on to the next question.
Oh, sorry?
You were able to select up to 5, and there are only 5 to select
Yes.
from. So.
Okay, so the next question is about the streams, the cold stream that we heard in some of the discussions. So The questions are streams responsible for star formation at high redshift? It's been argued as one of the possible mechanism of getting the gas into the galaxies, and is that actually playing a role? Is the stream stable enough? Is it disrupted? What's the role? Maybe yes and no questions. And let's see. Let's make that redshift of 2 massive galaxies that we heard a little bit about. So just focusing on some of the talk that we just heard in earlier sessions. So let's make this into a star formation in massive galaxy at redshift of 2, just to be specific. Okay, so we are closing. Last vote. Yeah, I think we're good. Yes and no. Wow, I think that's a good split. Anyone who wants to justify your answer for or against the cold stream possibly playing a role in star formation at high Z massive galaxies? Go for it.
Yeah, I mean, I guess the question is how much are they responsible, right? Like, how, to what extent? I don't know if they're responsible, like, to a very large extent, but, you know, just basic physics, right? Like, you need cold gas. Cold gas comes in from these streams, like filaments are thinner at high redshift, and that should have that should have some degree of effect. How much? I don't really know.
Any other thoughts? Go for it.
Yes, although I don't study streams, but another interesting thing I noticed from many talks is like when you are tracking stream, the stream doesn't necessarily penetrate towards to the star forming region. So it's hard to characterize, I would say, in this way.
Good point, good point. So that's a no answer. Maybe. Okay, any other thoughts about the role of cold streams? Anyone else? Okay. If not, maybe let's move on to the next question. Let's see. Okay. So we talked a little bit about the origins of SA tension being possibly a cosmological origin or possibly due to some baryonic effects. So this is not the yes/no questions, but there are probably other opinions about this. So let's open so this is a question for, and then maybe some of you are just sick of hearing about it. So that's an option, or none of the above. Maybe you have some other ideas for why we're seeing this tension. So the vote is open now?
Yes, it's okay.
We are getting close, so I will be closing in 2 seconds. And let's see what the audience says. All right. Okay, well, it's also somewhat split. Interesting to see that there are a lot of people sick of hearing about it. And some actually thinks that there's a cosmological signal in that tension, and majority actually thinks maybe it's a galaxy astrophysics, maybe none of the above. So let's hear anyone who wants to share your thoughts on your answer. Joe.
I buy your argument. For some time, including a paper that I hadn't seen yet that you mentioned, the cluster data is showing no tension at all. It's perfectly consistent with the expectation. And as you pointed out, the galaxy simulations and the way that they could affect S8, very uncertain. So it's almost certainly that we're not doing the complete astrophysics right, especially concerning galaxies and their environments.
Okay, thank you for sharing your thoughts. Anyone else who would like to chime in favor of that proposal? Maybe baryonic effects, or maybe that there's a reason to think there's a cosmological signal here. Or maybe we haven't seen enough data to say one or the other. Okay, anyone who wants to share? Yes, Phil, in the back.
Well, I'll just mention what we were talking about earlier as a plug. There's a student at Caltech, Isaac Cheng, who's working on following this up, but I think the challenge with the baryonic explanations is partly not ruining everything else, which is always the art. And the examples of the baryonic simulations that do a good job pushing the baryons out to megaparsec scales are things like the flamingos -8 sigma, and Daisuke and I were talking about this, where they, it's called -8 sigma in the papers because it is sort of a -8 sigma outlier in measurements of things like the gas properties in the centers of halos and in the more massive halos and things like that. But I think there's an easy understanding of that because the way they push the baryons out at large radii is they detonate a thermal bomb at the center and they just make the bomb stronger, basically. So it destroys everything in its path. So, the thing that the student is working on, that we've been thinking about and a number of other people have been thinking about, that Daisuke and I were thinking, is, are there gentler ways, maybe something like cosmic rays at large radii can push on the gas, maybe other, preventive feedback mechanisms, like what Renyu was talking about, but again, the challenge seems to be sort of, having feedback act on those scales without just blowing everything out from R = 0.
Okay, Frank, that's his hand up.
As someone who wasted a decade of my life on the S8 tension, I actually really liked very recent ideas that it may have something to do with the optical depth to reionization being wrong from Planck, and that's all there is to it. We may have to revision the optical depth to reionization as inferred from Planck and make it consistent with WMAP, and then a lot of the problems go away.
Okay, anyone else? Sure. Okay. Anyone else who wants to chime in on these questions? Maybe we can, if not, we can go on to the, do we have one more question? I think this is it, right? Okay, good. So I think we're a little bit over time, but I think this is a good place to stop.
Okay, sure.
All right. Yeah, thank you very much for everyone. And I guess we're meeting again at 9:30 tomorrow again? Yes?
Yes.
Wonderful.
All right, thanks everyone.
Thanks, everybody.